Hello everyone. In this video we are going to learn about a mathematical tool technique to analyze the efficiency of algorithms. Okay, as we discussed in the previous lecture, everything that you are going to learn in this course, in the data structure and algorithms course, is to write better programs. So to write better programs, you need to actually choose among different data structures which have, and how to choose between those data structures. This is just based on the fact that how efficient different methods can be implemented in all these different abstract data types or data structures. So when we are talking about the efficiency of algorithms and which algorithm is going to be more efficient in which situation, we need a measure to say that, okay, this algorithm is better than this algorithm. How can we say that, okay, you know that there are plenty of different ways to write a program that solve a problem, but they might actually be completely different than each other, and how can you say that, okay, this algorithm is going to work better, this algorithm is more efficient, this algorithm is faster, this algorithm needs less space. So we need a technique to do that, and that technique is going to be called asymptotic analysis, something that we are going to discuss here. You can actually, get this sense that when you are comparing different algorithms in terms of efficiency, we basically cannot rely on some details of the implementation, like on which computer you are running it, or in which programming language you have implemented that. We need a tool that helps us to analyze the efficiency of algorithms independent of all the details of the implementation. So just the essence of the algorithm, that this algorithm is going to work better than this one, this is going to be more efficient. It doesn't matter where you are implementing them. I mean, if you implement them in the same environment under the same condition. So basically this asymptotic analysis is going to be a mathematical tool. It is completely independent of the technical stuff, programming languages, machine, or anything else that you use to implement them. So the whole lecture here, I'm going to actually just talk about asymptotic analysis and why we care about that, just give an introduction about that. Then we talk about the quadratic and polynomial growth, the difference between them. I will talk about the primitive instructions and how we count the number of primitive instructions to be able to get some sense about how much time would take for an algorithm to be executed. And I will introduce two notations, famous notations, big O and big theta. I'm sure that you have heard about at least big O in COMP251 before. So here we are going to basically learn more about these notations and see the exact mathematical definition of them. Okay, so the main question that we wanted to answer here is that we want to know how can we compare different two algorithms that both of them are solving the same problem. So assume I have a problem, I have written two different algorithms for it, and I wanted to analyze and compare them and say that, okay, which one is going to be better. Better means that it's more efficient, it's going to be faster when I'm actually implementing them. Of course, one way is that I implement each of them using one programming language, the same programming language, and execute them exactly on the same machine under this completely the same condition. You don't have any other program, for example, running in the background. They have access to the same amount of space, memory, RAM, You don't have, CPU is not running any other threads or process in the background or anything else. You should actually just make sure that the condition is the same for both of them, and then maybe you can actually just compare them. You can see that this is going to be very complicated. First, you have to implement both of them using in the same programming language, so you have to spend some time on that. You have to make sure that the condition is completely the same, so it is going to be a fair comparison. But all of these are going to be, very, too hard to achieve and very error prone. So the way that we are going to analyze the algorithms is, I'm going to introduce another way for you that is going to be much easier and way more accurate. So you can actually confidently say that, okay, this algorithm is going to be better than this algorithm because I know that the time complexity of this one is this and this one is the other one. So this is what we are going to do using the asymptotic analysis. So when we are in fact analyzing the efficiency of algorithms, we need some kind of measure some variables that we compare the efficiency of our algorithms in terms of that variable. And it actually just gives you this sense that, for example, your algorithm is going to work on something, right? On some data. So the size of your data, your input data, is going to affect how much time your algorithm would take. For example, assume you have a list of numbers and you wanted to sort them, right? If you have a list of 10 numbers, it's going to be completely different than sorting a list of 10 million numbers, right? So the size of the input is going to affect how much time would take your algorithm to be executed. So that variable is going to be the variable that we just actually, we analyze the efficiency of our algorithms in terms of the size of input. Okay, so sometimes you just have one variable, just like, for example, that sorting algorithms that they are sorting in, for example, items stored in an array, or for example, you have an array, you have a data structure, you are storing some items inside that, and you don't know how many items at each time, because you are actually adding or removing some item from this data structure. So the exact number of items in the data structures is not clear, but you know that at most, for example, n number of items will be inside, will be at each moment will be stored in your array, for example. This is going to be a variable. Or for example, you are multiplying, you're working on a matrix which is a square matrix with dimensions n to n. So in all of these examples, that you just have one variable. In fact, in many examples you only have one variable, but in some examples you have even more than one variable. So it doesn't really matter. You should actually keep track of all the variables that define the size of your input. For example, if you're working over a graph, you know that a graph, you don't exactly know how many nodes and how many edges are there. The number of edges is going to be, for example, at most the a square number of nodes. Okay, but it's not always the case. So if you are working in a graph, usually all the algorithms defined over the graph, they analyze the efficiency of algorithms based on two variables, the number of nodes and the number of edges. So both n and m, these variables are going to be matter. Or for example, if you are multiplying two matrices, one of them is of dimension k to m, the other one m to n. Here, in fact, you have three variables, right? M, n, and k. So you should actually keep track of all of these variables. So there are plenty of different examples. I'm just actually trying to tell you that we analyze the efficiency of the algorithms. We analyze the how much time would take for an algorithm to be executed based on the input size. Okay, so it doesn't matter at the end. What we are going to actually discuss is that, okay, if the input size is n, the time complexity would be something in terms of n, right? In terms of that variable. Okay, so the first step in analyzing the efficiency of the algorithms is basically when we are analyzing the efficiency, we wanted to know how much time it would take for an algorithm to be executed. But we want this to be independent of the machine that I'm working on. Maybe I have a very old machine, or you have a very, new machine that of course, these new machines are going to be much faster, right? But when I'm actually talking about how much time it would take for an algorithm to be executed, I don't care about the exact time, because that would depend on the machine that you are running your algorithm on. So I need to define another measure. That measure is going to be counting the number of simple instructions, or primitive, we call it actually primitive instructions. This algorithm would, for example, take this many number of primitive instructions to be executed. What is a primitive instruction? A primitive instruction in the modern computers, by modern I mean the regular computers that you have here. I don't want to actually go to the details, but anyway, those computers that have a CPU unit and also have access to a memory that is fast access memory, we call it random access memory, and the primitive instructions are going to be all the Boolean operations, logical and or not, X or all of them, comparison operators, over the primitive data types. So when you are comparing two numbers, basically when you are comparing two numbers or two Booleans, or some primitive data types, less than, greater than, equal, not equal, all the arithmetic operations, all the bitwise operators, and reading and writing to the memory. So these are the primitive instructions in any modern computer. It doesn't matter how old or new is your computer, if it is following the word RAM model, that it has actually a CPU, some accessing to some memory, and some register, and that computer architectures that you have learned under the name of von Neumann. So basically any computer that we are working on. So in COMP251, if you take it, you would see that there are some other machines that they are computing machines, but they are not like the modern computers that we are using now. So, just let's forget about all these details. What I wanted to actually just say that is the primitive instructions are going to take 1 unit of time on your computer. It doesn't matter if your computer is very old and, for example, 1 unit of time would take, for example, a millisecond, or you have a very fast machine that 1 unit of time on your machine would be, for example, 1 microsecond or something. Okay, it doesn't matter what is the machine that you are working on. I just wanted to know that how many simple instructions, how many primitive instructions your algorithm would need to be executed. Okay, and remember, we actually just talked that we analyze the algorithms based on the input size. So when you are counting the number of primitive instructions, this will definitely depend on your input size. The result is going to be a formula, a function in terms of those variable, that input size variable. So let me actually show you what is how we can actually count the number of simple instructions over a very simple example. Let me show you a couple of examples here. Okay, I have this simple piece of code. You can see that this is just basically a for loop that iterates and adds on some actually numbers from 0 to n. Okay, so how many primitive instructions it is required for for this piece of code to be executed. It doesn't matter on which machine you are actually executing this program, right? So what are the primitive instructions? Reading and writing to the memory. So basically, when you are assigning something to a variable, this is going to be a simple instruction. Multiplication, all the arithmetic expressions, each one is going to be a simple instruction. Comparison is going to be a simple instruction. So here I can count these simple instructions, right? Let me okay, so this is going to be one simple instructions. Here I am actually assigning the 0 to some, and here I have one simple instructions when I'm initializing I. I have a comparison, right? Be careful, this is a for loop, right? It doesn't really matter how I'm actually writing this loop. If it was a while loop or a for loop, doesn't really matter. The thing is, I wanted to count how many instructions will be executed. I have one comparison, but these comparisons will be executed more than once, right? I will be initialized to be 0, and then you are actually increasing it in this loop, and the next time it will be actually compared to n. If it is still less than n, this loop will iterate, right? So the total number of instructions here is going to be 1 for the initialization, right here, 1 for this initialization. This comparison is going to be executed more than once. How many times this one is going to be executed? N number of times you will execute this, right? For example, if n is 2, it will be executed 2 times. If n is 10, it will be executed 10 times. This increment over I is also going to be executed n times. Because why n times? Because you initialized I to be 0, and you are increasing I each time by 1. So if, for example, n is 10, I will start it from 0, and then it will be 1, then it will be 2, then it will be 3, until it reaches to 10, right? So the number of increments is going to be n, the number of comparisons that I have is going to be n, and the body of this loop is going to be executed again exactly as the number of iterations of this loop. So this is going to be n as well, right? So these are the total number of instructions that I need to execute. I will add them up, and it gives me a formula. This is going to be the time function for me. And as you can see, this is a function in terms of n. N is our input size, right? I don't know what is n, but the execution of this code will depend on how big is n. So that's why I have to keep this variable n. I can say that, okay, n is equal to 10, n is equal to 1,000, n is equal to 10,000, 10 million. I don't know what is going to be n, right? So this is going to be your input size. So you keep your time function in this way. So let's do another example. This time, as you can see, I have 2 loops, 2 nested loops. So it might actually look a little bit more complicated. I have one initialization here, right? I have one initialization here, n number of comparisons for this one, and increments for this. But be careful. Why I am saying the number of iterations of the outer loop is going to be n, and the reason is that you initialized I to be 0 and you increase I by 1 each time. If you are actually, your loop, your iterator is going to change in a different manner, the number of iterations is going to be different, right? So be careful about that. So in this example, still the number of iteration is n, so I have n comparisons here, n increments here, and there is another loop. This loop is going to be inside this loop, right? So for one iteration of the outer loop, I need to actually count that how many times these instructions are going to be executed. And then I need to multiply the whole thing inside. I need to multiply the whole thing inside n, because n is the number of iteration of the outer loop. So in total, I can say that, okay, one instruction here, one initialization here, one initialization here, n number of comparisons, n number of comparisons here. This loop, if I just isolate it, forget about that this is inside the other one. One initialization here, comparison, increment, because you started from 0 and you increment by 1, so the number of iterations here is going to be n. So this is going to be, so basically I can write it as n number of iterations there and n number of iterations for this one to increment this. So this is going to be the total. I should probably write this one as well, right? So I know that the total iterations for this part is going to be 1 plus 2 n plus n. This is for the loop, the body of the loop, and the whole thing needs to be multiplied to n because this is inside another loop. Okay, so if you actually know, if you add all of these, you would get another function, and now you can see that this function is completely different than the previous function. This is a quadratic function. The previous one was a linear function. Okay, so let's see another example. Again, here I have a loop. I have one, forget this one simple, one initialization here, so one instruction there. And then I have, okay, one initialization here. You are comparing I to n, but be careful. This time, the way that I'm changing the iterator is not just incrementing it by 1. I am increasing the I, kind of exponentially, because I'm multiply it by 2 each time. So I is 1 in the first iteration, I will be 2 in the second iteration, I will be 4 in the third iteration, I will be 8 in the fourth iteration, right, 16, and so on. So each time you are just multiplying it by 2. It is increasing exponentially in terms of, 2, okay? So the number of iterations will be different. For example, if n is 16, the number of iterations basically is going to be 4, right? But still, there is a relation. There is actually a formula. I can find a formula for the number of iterations. So the number of iterations this time is not going to be n, but it is going to be log of n, right? Because I am log of n in base 2, because each time I am multiplying I by 2. So the main thing about this example was that you understand the number of iteration of the loop is going to be log of n in base 2, not n like these examples. In these examples, the number of iterations would depend on n because you are incrementing I by 1. You started from 0 and you increment I by 1 each time. Here you are increasing the size of I by multiplying it to 2. So it is much faster. So it actually gives you this sense that when you have a loop like this, the loop is going to iterate definitely much less number of times, right? So it's going to be much faster. If you have a piece of code like this one, this is going to be clearly much faster than this piece of code, right? This loop is iterate over all the numbers. This one just iterates over the powers of 2. So this is going to be to iterate way less number of times. So this code, if you have a code that has a loop like this is going to be much faster. So, but forget about all those. Let me actually just stick to this fact that we are counting the number of primitive instructions. Okay, so here the formula that I got is this one. Some coefficient multiplied by a log of n plus some another actual coefficient, basically. Okay, let's see another example. How many primitive instructions I would need if for this function, this is a function that basically search for the largest item inside a list. Just assume that you have an array and you are looking for the largest item in that array, an array of integer numbers. Okay, so the first question that I have here for you is that what is the input size here? Basically, you can see that your input is going to be an array. I don't exactly know what is the size of it, right? But everything will depend on that size, how many items you have in that array. So I can actually just assume there are, as I'm actually writing it here, there are n number of items in your array. So again, this is going to be your input and your time function will depend on this variable. Actually, you write your time function in terms of this variable, n. So let's actually look at how many simple instructions I need. Again, I have one initialization here. Again, you know that accessing to different indexes in array is going to be constant. So we say that this is just accessing to the memory, and this is going, you just consider it as a primitive instruction. So it's just like you are accessing to a regular variable if you have an array. So again, I have initialization here. I have some comparisons and some increment. So can you tell me that how many iterations I have in this loop? You can see that I have started from 0. I am increasing the iterator by 1 each time until it reaches to the size of the array, which is n. Okay, this array length is going to be n. So the number of iterations clearly here is going to be n. One question that one thing that is you didn't have seen it before is that I have an if statement here. The if condition itself is a comparison. It is a simple instruction and it is a primitive instruction. And in each iteration of the loop, definitely this comparison will be executed. But how about this line? This line is only going to be executed whenever you see a new maximum item. So if your items have been sorted in increasing order, each next actual index that you check is going to be bigger. So this, then the execution of this line will depend on how the numbers have been stored in your array. So I don't know how many times this line will be executed, right? it will depend on the input. It is going to be executed something between 0 and n. If the maximum item is going to be the index 0, it's not going to be, this line will never get executed, right? So either between 0 and n, it will be executed. But the thing is, even if I don't know what is going to be the number of times that I execute this line, I still can write the simple instruction in this way, right? Because even if it executed 0 times, it the total number of instructions is going to be something like, maybe I'm not, just assume that, for example, it will be executed 0 times. It's going to be to have two extremes, right? If the number of execution of this line is 0, if it is, for example, n. In this case, the time function is going to be something like, 3 plus 3n, something like this, right? And if it will be executed, this line is going to be executed in every iteration. So basically it will be executed n times. The number of iterations, the time function is going to be, for example, some 3 plus 4. And maybe I'm not exact in these numbers. I just wanted to tell you that all of these are going to be, I can actually write all of them in this form, right? This is going to be a linear function. I just wanted to tell you that I don't really care that if the coefficient of n is, for example, 3, or if it is 4, or even if it is 10,000 or 1 million. In terms of, comparing the efficiency of the algorithms, the asymptotic analysis. And then, I will actually explain why I don't care about the coefficients. The main thing that I care here is that the time function is going to be a linear function, some cn plus c prime. Okay? So let me actually just show you that why those coefficients are not really important. And what is important is that, for example, this function is a linear function. But it is completely different than something like this. Okay, this is going to be quadratic, this is linear. Okay, let me actually show you the example. Suppose you have written an algorithm for a retail store that will actually do the processing of the inventory. So assume that you are using a computer that takes, for example, 10,000 milliseconds for to be actually loaded, and so in the initial part of the work would take this much time. And then for each transaction in the store, your algorithm would take 10 milliseconds to actually process that transaction. So if the number of, if you are actually, how much time would take your program to process the whole stuffs of the store inventory, it would take this much time for the initialization, and for each transaction it would take 10 milliseconds. So in total this is going to be this many milliseconds. So here it is, now it actually would make sense to you that why I am saying that this is important for me, that, for example, this is going to be a linear time function. The fact is, you have two terms in your function, right? 10,000 for the initialization, and 10 millisecond multiplied by the number of transactions for each transaction. You don't know how many transactions is going to happen every day. But in general, you would actually expect that, okay, this retail store is going to have quite a lot of number of transactions. right? Maybe 1 million number of transactions, 10 million number of transactions. So it is very clear that this term is going to be way more important than this term, because this term is going to be constant. It doesn't really matter how many items are going to be processed. It is always going to be 10,000. Not only it is not important because it is fixed, but also, for example, later on when you actually, for example, next year you are going to get a faster computer to do this program, to execute this program. And in that program, not only this, this initialization, the loading the program would take less time, but also even this coefficient is not important. In your new computer, this coefficient is going to be actually less, but you are not really changing n. The number of transactions is something that you cannot touch it, right? So it will be important to have this fact that, okay, this algorithm is going to take linear amount of time in terms of the number of transactions that it processes, okay? And it would be very important that if you had another algorithm that would take, for example, I don't know, something like half a millisecond multiplied by n power 2 plus, I don't know, 10, something like this. If you have another algorithm that would take this amount of time, you would definitely get this sense that this algorithm is going to be way better than this algorithm. Why? Because the coefficients are not really that important, but the time will basically depend on these terms of n. Okay, so this is exactly the something that we discuss in asymptotic analysis. Okay, let me actually show you this example. Before we go to the asymptotic analysis, I just wanted to actually finish this this part, that to be able to analyze your algorithm, you have to first find the time function for your algorithm. But when you are actually discussing the time function for your algorithm, don't be very, picky about those coefficients. Something that is important for me is that, for example, if you have a loop like this one, your time function is going to be logarithmic. If you have a loop like this one, your algorithm, your time is going to be quadratic. When you are discussing a loop like this one, your time function is going to be linear. Okay, so this is something that is important for me, and now you will see that why. Okay, after you got your time function, after you calculate your time function for your algorithm, now it's time to actually analyze and compare those time functions. Okay, assume that you got two algorithms. One of them, the time function is this, and the other one, the time function is this. How can I say that which one is better? So you would probably say that I need to just look at the diagram of these two algorithms, these two time functions, and say that which one is better. This is the diagram, the blue one is the diagram for the g of n, and this one is the diagram for f of n. Which one is better? It's not quite clear, right? Because at the smaller values, this one, the blue one, is going to take more time. On the larger values, the red one is going to take more time. But the fact is, if you look at the diagram of these two functions on a large scale, they look pretty much the same, right? Even this diagram that I'm showing to you, it's just to size 1000. 1000 is not really that big. You should, when you are actually analyzing the time complexity of your algorithm, you should assume that n approaches to infinity, because n can be really big. The size of the input can be really big. You are not working on some fixed problem size. N is going to grow. You should think about n as something that grows, and you don't have any control over the growth of n. So when you are comparing two algorithms that one of them has the time function f of n and the other one has the time function g of n, basically I'm going to tell you that it doesn't matter which one you are choosing. The efficiency of both of these two algorithms is going to be the same, because the growth ratio of them is going to be the same. Both of them are going to have quadratic growth ratio. Okay, let me show you another example. Compare these two, f of n and g of n. They are again two polynomial time functions, but the leading term is much bigger than the previous cases. It's going to be n power 6, and this is just n power 6. The other one is not only has this n power 6, it had a lot of other actually terms of n. Okay, when I'm looking at the diagram of these two functions, I can't really compare them that much. Sometimes the blue one is smaller, sometimes the red one, and they are actually just going to have different behaviors. But again, if I'm looking at a larger scale, they look pretty much the same. Again, because the growth ratio of both of them are the same. The leading term in the polynomial expression that you have is n power 6 in both of them. So again, if you have two algorithms that has these two g of n and f of n time function, I would say that these two algorithms are going to have the same time complexity, because when the size of n is growing, the difference between the time that takes for both of these two algorithms is very small, and it's completely negligible. The growth ratio of both of them are the same. But if, for example, you had if you are comparing something like, for example here, if you were comparing this, for example, f of n to be n square and g of n to be linear, for example 10 multiplied by n, something like that, the diagram for 10n would be something like this. And now you can see that this one is going to be the behavior of this function, the growth ratio of this function, this g of n, is going to be way slower than f of n, which is n power 2, right? So it's clear that g of n is going to be, better, because it is slower. It's going to, when I'm saying it is slower, the time function is slower, but your algorithm is going to be faster, right? Your algorithm is going to take less amount of time. This diagrams is going to show the amount of time that would take to execute your algorithm. So this is going to be way worse, because it's going to take more time. Okay, so all of this is the idea behind the asymptotic analysis, and how they don't really care about the coefficients, but they care about the growth ratio of the functions. Now you can see that they are really abstracting away all the details and just think about the essence of your algorithm. This is actually the summary of when you have some polynomial growth ratio. We basically care about the leading term in your function. So in those examples that I showed you, in the first case we had the both terms was n square. In the second example, both case was n power 6. And so the growth ratio of both of those algorithms were the same, and we say that okay, they are going to have the same behavior. So now it's time for actually introduce that big O notation. Okay, I'm going to first define the mathematical definition of big O here. We would say that a function f of n is in big O of g of n. Be careful about this notation. It's saying that f of n is in big O of g of n. So basically O of g of n, you should think about it as a set. As a set that it has a lot of actually functions. And what is the definition? We say that a function f of n is in big O of g of n if I can find two constant values n and c, such that for big N and C, such that for all the values of n greater than big N or capital N, always f of n is less than or equal to c multiplied by g of n. So if it is the case, if you can find these two constant values, be careful, n and c, both of them should be constant. So it doesn't matter if it is, for example, 10 million, if it is 0.5, it doesn't matter how big are the numbers, it should be constant. It shouldn't be something depending on n. So n and c cannot be something like, 0.5n. This is not constant. Okay, by constant I mean just a fixed number. Okay, so if it is the case, if f of n is in big O of g of n, it means that the growth ratio of f of n is no greater than the growth ratio of g of n. It's just like g of n is going to be an upper bound for f of n. Definitely the growth ratio of g of n is going to be greater than or at least equal to the growth ratio of f of n. So let me actually just show you some example. In that example of inventory store, remember we found the time function to be something like this. We say that the f of n is in, I can say that f of n is in big O of n. Why? Or basically I can say that the time complexity of that algorithm that we wrote for the inventory store is in big O of n. Why I can say that? Because I can find two constant values, c equal to 20 and n equal to 1000, so that from the value 1000 to infinity, always this is going to be, this one is the the diagram for f of n, and this one is the diagram for 2 multiplied by n. You can see that I needed to find that c of n, right? That so that for all the values of n greater than 1000, this is that big or capital N. For all the values of n greater than 1000, always f of n is going to be less than or equal to c multiplied by g of n. C is a constant, this is 20, I just multiply it to n, right? So g of n was n. So I can say that f of n is going to be linear, or f of n is in big O of n. Okay, let's see another example. It doesn't matter how big is the coefficient of your function, because I can say that f of n equal to 1 million n is in big O of n. This is going to be linear. Why? Because I can find a bigger constant to make f of n always less than c multiplied by that g of n. So now it actually just gives you this sense that
when we are writing big O of n, in fact, we are talking about a set of functions. All the functions that are linear, all the polynomial functions which are linear are going to be a part of this O of n. And when we are writing it as O of n, it doesn't really matter if you write it as O of 2n, if you write it as O of, I don't know, 10n plus 1000 plus 100, sorry. All of these are going to be the same. But in math, we always go with the simplest forms. So this is going to be representation for the set of all those functions which the growth ratio of them are bounded by linear. But be careful, O of n is an upper bound. It is just talking about, limiting the upper bound for your growth ratio. So can you answer this question for me? Can I say that f of n, which is going to be equal to just n, is in big O of n power 3, big O of n cube? Can I say this? The answer is yes. Why? Because I can actually find c equal to 1, n equal to 1, and say that always n, for all the values of n greater than 1, n is less than or equal to n power 3. That is right. And so this is because big O is an upper bound. This is going to tell you that the growth ratio of n power 3 is greater than the growth ratio of f of n. So that's why big O is not, mathematically, this is not exact, growth ratio. It doesn't show the exact growth ratio. It just shows you the upper bound. Although when you are actually looking at the textbook and different actually courses in computer science, you can see that usually people are using actually big O. But I'm just trying to tell you that big O it's not wrong to use big O, but big O is not exact, notation to show the exact growth ratio. Big O shows the upper bound. That's where we actually introduce the another, notation that we call it theta. But before I actually go to the explaining the theta notation, I'm going to actually show you a table of all the important big O sets that we have. The slowest set of functions, which is going to be the best time complexity that you get, is going to be the constant, that we show it as O of n. So if your algorithm is going to take a constant amount of time, it doesn't matter how big is it. For example, your algorithm is going to take, I don't know, 1 million number of simple instructions, but you can see that it doesn't depend on n, So this is important. So in all of those cases, we would show it as O of 1 and say that this is going to be constant. If you have an algorithm that works in constant amount of time, that is the best. That is the best that you can get. So this is going to be the most efficient set of algorithms. After that, the well-known algorithms that we have are those algorithms that works in logarithmic time. Then those algorithms that works in square root of n, and those algorithms which are in linear. And now you can actually see that those algorithms that works in linear are going to be less efficient than the algorithms that works in square root. These are going to be less efficient than the algorithms that works in logarithmic time. So as you are going down, that the growth ratio is increasing. And because big O is actually showing you some sort of superset, this is an upper bound, you can actually see that if I show all these sets, it's going to look like this. The smallest set that I have is going to be this set of constant time. If it doesn't matter how much time it is taking, as big as this one or as small as this one, the growth ratio of all of them are going to be constant. They don't depend on n. Then after that, it is going to be the set of all the logarithmic functions. And it is important to know that the logarithmic functions doesn't really depend on the base. If it is the base 100, 2, 3, whatever, it's going to be the same. And then you are going to actually go to the linear functions. Again, the coefficient is not important. If the leading term is just linear, all of them are going to be in the same set, linear. And then after that, n square, n power 3, n power 4, all of them are going to have different actually levels, and then the exponential ones, and so on. So I didn't really have time, space to draw all of those. But here it actually shows you that, for example, n log n is going to be better than n power 2. And it is clear, right? Because it has one term n, the other one log n. It has two terms n to n. So that's why this is going to be an upper bound for n log n, n power 3. And about the exponential ones, you should be careful that each of these are going to define a different level. I'm here showing it to you that 2 power n is different than 3 power n. This one, the growth ratio of this one is going to be exponentially slower than the growth ratio of this one. Okay, so the next notation that, this one is very similar to big O, but in terms of the mathematical definition that we write, but this is exact growth ratio. This is called big theta. So again, we say that f of n is going to be in big theta of g of n. If I can find this time 3 constant times, all of these constants should be positive. Be careful, these constants should be positive. So that for all the values of n greater than capital N, I can find these two constants C1 and C2 such that C1 multiplied by g of n is less than f of n and C2 multiplied by g of n is greater than f of n. So it's actually just telling you that the growth ratio of f of n is going to be exactly equal to g of n. If you can show this, you will say that the growth ratio of f of n is exactly equal to the growth ratio of g of n. So let me actually show you an example. F of n equal to, for example, 1 million multiplied by n. We say that this is going to be in theta of n. Why? Because I can find two constants, 1 and 1,000,001, and for all the values of n greater than 1, I can say that f of n is going to be greater than or equal to C1 multiplied by g of n and less than C2 multiplied by g of n. Again, for theta of n, basically theta of n showing a set of functions. All those functions like 2n, 3n plus 100, 0.5n plus 10 power 10. All of these functions are going to have the same growth ratio. And you can actually write all of these, but in math, theta, not O. But in math, what we wrote is just the simplest form. We wrote it as theta of n, and we say that all of these functions are going to have the same growth ratio as t of n. And t of, basically, n is going to be the representative of this set. If I'm going to show you that the same, actually, this is the difference between big theta and big O. Big theta is not showing the super set, is not showing the upper bound. Big theta shows the exact time complexity. So, big theta will kind of create an equivalence relation. So it partitions the set of all possible functions into disjoint set. This is the set of linear functions. This is the set of n-square functions. This is the set of constant functions. This is the set of logarithmic functions. This is the set of 2 power n functions. Okay, and there is no relationship between these sets. They are completely disjoint. You except this fact that, okay, yeah, this is going to be an upper bound, but no relationship based on the big theta. So big theta doesn't actually create a relation between the functions here and the functions here. Unlike the big O, that you can see that it shows a kind of a superset relationship because it represents the upper bound. So now using big theta, you can actually just see that although we could say f of n equal to n is in big O of n power 3, you cannot say this. This is going to be wrong. And the reason is that you cannot find a constant that if you multiply to n power 3, it makes it smaller than n. And it is very clear. The growth ratio of n is not equal to growth ratio of n power 3. The growth ratio of n power 3 is way bigger than the growth ratio of n. So again, we are going to have the same the same common classes of the functions, those ones which are constant, those ones which are logarithmic, linear, n log n, n power 2, n power 3. And again, I'm emphasizing that when we are talking about the exponential functions, they are completely separate classes in big theta, right? This is a class, this is the class of 3 power n, this is the class of 2 power n, and the base of these exponential time functions are going to be important. Here, this example basically shows you something that I am actually showing you the diagram of 2 power n, e power n, this natural number, and 4 power n. So be careful when you never can say that a power n is in theta of another exponential function b power n, unless a is equal to a is exactly equal to b. If a is not equal to b, this is completely wrong because the growth ratio of the exponential functions are completely different. But this is not the case for the logarithmic functions. Basically, you can say that log of n in base b is equal to log of n in base a or anything else. So log of n in base 2 has the same growth ratio as log of n in base, for example, 100. Why this is the case? Because let me actually just prove it to you that log of n, for example, if remember I wanted to prove that log of n in base b is in big theta of log of n in base a. Okay, it doesn't matter what is a and what is b. I'm going to show you that it is always correct. How? Because I can convert this one to this one only by multiplying it to a constant number. Let me show you this. Log of n in base b, I can write it, this is just from, again, the discrete math. I can write it as log of n in base a divided by log of n, log of b in base a. Okay, so now if I simplify, this is going to be log of n in base b multiplied by log of b in base a is equal to log of n in base a. Okay, what is this number? This is going to be a constant, right? because b is constant, a is constant, log of b in base a is going to be a constant. So basically I showed that I can actually write log of n. I can find two constants to be the, I can find two constants, c1 log of n in base a less than or equal to log of n in base b less than or equal to another constant log of n in base a. Okay, if I can prove this, I can say that log of n in base b is in theta of log of n in base a, right? The growth ratio of them are the same. When we are actually saying that the growth ratio of two functions are the same, we are saying that the difference between them is going to be some constant. I just need to multiply it to some constant, and they are going to have the same value. So I think I am done with this lecture. Basically, we have discussed everything. I just wanted to, go back and for all of those pieces of codes that we discussed at the beginning of the lecture, let's find the big O notation or theta notation. Although I have defined the big O notation and theta notation here, and they are different, you should know the difference between these two. When we are actually talking about the algorithms, in many cases I would probably use big O instead of theta. It's just because in many textbooks they are using big O. It is not wrong to use big O. I'm just trying to tell you that it would be more precise if you use big theta notation. Okay, anyway, let's just go back and cover these examples. Okay, if I have a piece of code like this, I can say that the big O and the time complexity of an algorithm like this would be linear O of n. For this one, remember what was the time function? The time function was a square time, right? So I can say that this is going to be the big O of n power 2. So this is going to be n square. Remember this algorithm, this piece of code? The number of iterations was depending on log of n, right? The time function, and then it is going to be in big O of log of n. I have two more examples here. Okay, let's just discuss them. You have you have an algorithm. I'm going to find, sorry, I got pretty tired here. You have a set of points. You wanted to find a pair, the closest pair among all of them. Okay, you have in a 2-dimension space, you have some points. You wanted to find the pair, the closest pair, basically. Okay, how you are going to find the closest pair? There are different algorithms to do this, but I'm going to just discuss the simplest algorithm. The simplest algorithm that might come to mind is that you find the distance between all of the pairs and just find the one which has the minimum distance, right? How many pairs of points you are going to have? If you have n points, the number of pairs is going to be n2 n minus 1 divided by 2, right? This is going to be the choice of 2 of n, number of points. And calculating the distance between 2 points, you can just assume that you have a function to calculate that. You know that if you have 2 points, x1, y1 and x2, y2, the distance between these 2 points can be calculated as x1 minus x2 plus y1 minus y2. Okay, This is the formula that you have to calculate. And you can assume that it had been actually implemented as this function distance. So now can you actually tell me that how much time this function would take to be executed? It is going to be constant, right? I can say it, write it as O of n. The reason is that you are just actually subtracting, sorry, I forgot the powers of 2 here. You are subtracting x1 from x2, you actually multiply it by itself, you calculate the power 2 of that, the same for this one, and then you calculate the square root. These are all arithmetic expressions, so the whole amount of time that would take to execute the distance between 2 points is going to be constant. And you can see that I have 2 for loops. The first one is going to iterate over all the points. The other one is going to iterate over the indexes from I plus 1 to the end. So to check all of these pairs of numbers. Okay, so and whenever you find a distance, a pair of that has the smallest distance, you would update this minimum distance thing. So the total time complexity here, if you just think about, you don't need to implement this, and you don't even need to calculate to write down the exact code here. I can just simply discuss here that the number of iterations, the number of times that I would calculate the distance between 2 points is going to be n to n minus 1 divided by 2. And I need to calculate distance for each one. It's going to take some constant time, right? And you just do some comparisons here and update. So in total, it's going to be some constant amount of time multiplied by this many number of pairs. And if you simplify this formula, you can actually get something like this: n power 2 plus cn. You can actually just have some other a formula like this. It is clear that this formula is telling me that the time complexity of this algorithm is going to be n power 2. Usually when you have actually 2 nested loops, that the although this inner nested loop, the number of times, the number of iterations of the inner loop would depend on the iterator of the outer one, but still it would linearly depend on the outer loop. That's why it actually makes it linear, but it makes it the whole thing n square. But let me actually just show you the, here you can find the exact time function or the number of primitive instructions that we have, and it actually just show you that how the number of instructions would depend on the value of I, but at the end it doesn't really matter, because the number of iterations in total is going to be the summation of all these numbers, which is going to be from 0 to n. And we know that the summation of all the numbers from 0 to n is going to have this formula. N to n plus 1 divided by 2, right? That's why it would be actually n square. There's another algorithm here that I would recommend you to definitely actually just read the algorithm and try to find the time complexity of this one. This is very interesting. You can see that again I have 2 nested loops, but be careful. Not always the 2 nested loops are going to have the n square time complexity. You should be careful that what does your algorithm do exactly. So execute your algorithm over, for example, an input like this, and see that how these two loops are working, and at the end you would see that the time complexity for this function, this algorithm, is going to be linear. So yeah, be careful that not always nested loops are going to give you n square. You should always actually take care that how many iterations all these loops are going to iterate. Okay, I am done with this lecture. Here is just actually showing you the difference between the quadratic and exponential algorithms. Definitely when we are actually talking about the exponential, the quadratic ones, or they are going to, so for example, n power 2 is going to be way better than 2 power n, because the exponential time functions are going to grow very fast. I have actually a lot of extra slides in this lecture that you can study them. I will upload everything on Blackboard, but I don't really want you to know all of those details, but they just actually probably give you a better insight. If you are interested, it helps you to actually study more than what we have discussed here. This is going to cover chapter 5 of your textbook, and you can basically find a lot of resources online about the asymptotic analysis. There are many actually good resources available. So I'm going to finish this lecture